We went to the moon. We landed human beings on the surface of another world. We brought them home safe. And we did it 6 times. So going to Mars, that's just the next step, right? Same basic idea. Just a little farther away, a little more fuel, a little longer trip. I mean, we did the hard part already. Mars is just further down the same road. That is completely wrong. And I'm going to show you exactly why. The moon and Mars are not the same problem at different scales. They are fundamentally different problems. And the difference is not the kind of thing you fix by building a slightly bigger rocket. The difference is mathematical. It lives inside an equation, and that equation is merciless. Let me take you through it. Getting to Mars is hard. Landing on Mars is really hard. But getting off Mars and coming home, that is a different kind of hard. That is the kind of hard where nature says no, and you have to figure out whether it really means it. First, let's agree on what a rocket actually does. A rocket works by throwing stuff out the back. That's it. You throw mass in one direction, and by Newton's third law, the rocket goes the other direction. Every rocket that has ever flown works on this one idea. Simple. But there is a devastating catch. The fuel you're going to burn later, you have to carry it now. And carrying it now means your rocket is heavier now, which means you need more fuel to accelerate all that fuel, which means the rocket is heavier still. It's a vicious, unforgiving spiral. There's an equation that captures this spiral perfectly. The change in velocity you can achieve, your delta V, equals the exhaust velocity of your engine times the natural logarithm of the ratio of your full mass to your empty mass. That's it. Delta V equals exhaust velocity times the log of the mass ratio. If you've never tangled with logarithms, let me explain what this means. If you need twice the speed, you need much more than twice the fuel. The relationship is exponential. Going from 3 kilometers to 6 kilometers doesn't double your fuel. It triples your mass ratio. At 9 kilometers, your rocket is 95% fueled by mass. This is what engineers call the tyranny of the rocket equation. Let me give you an analogy. Imagine a road trip across a desert with no gas stations. You have to carry all your gasoline with you. But gasoline is heavy. Carrying that extra weight means you burn more gasoline. So you need extra gasoline to haul the extra gasoline. Each new gallon helps a little, but eventually adding more barely helps at all because the fuel is mostly being used to carry itself. That's the dilemma rockets face. The Saturn V, that magnificent machine that took us to the moon, was about 85% fueled by mass at launch. It weighed about 6.5 million pounds. The part that actually went to the moon and came home weighed less than 1% of the total. All the rest was fuel and the tanks to hold it. The entire design was about getting rid of mass as fast as possible. Use it, dump it, move on lighter. The equation forced that design. Now let's talk about the moon trip. The delta V to get from Earth's surface into low Earth orbit is about 9.5 kilometers s. From low Earth orbit to the moon and back, the additional delta V is roughly another 6 kilometers s. The lunar module was very light because the moon's gravity is weak and it has no atmosphere. They left half of it behind on the surface. Every decision was about saving mass, and it worked. The total delta V budget for Apollo was roughly 15 to 16 kilometers. The Saturn V could just barely do it. So now Mars. The first thing to understand is how far away it really is. The moon is about 3 days away. If something goes wrong, you can turn around. Apollo 13 proved that. Mars is not 3 days away. At its closest, it's about 55 million kilometers. You have to launch at just the right time, follow a curved path, and arrive about 8 or 9 months later. 8 or 9 months in deep space with no possibility of turning around. If something goes wrong, you are in a metal tube hurtling through the void, and your only options are to fix it yourself or die. There is no abort. There is no safe harbor between here and there. The nearest human being not on your spacecraft is getting farther away every day. Let's talk about delta V. From low Earth orbit to a transfer orbit to Mars is about 3.6 kilometers s. Then you need to slow down when you arrive, another 1 to 2 kilometers s to get into Mars orbit. Then you need to descend to the surface. And this is where Mars starts to show its teeth. Mars has an atmosphere, but it's a terrible atmosphere. It's about 1% the density of Earth's. Standing on Mars is like standing at 35 kilometers above the Earth. It's thick enough that you need a heat shield, but far too thin to stop you. A parachute can only slow you to about 200 mm/force. That's a crashing speed. So after your heat shield and parachute do their job, you then have to fire rockets to do the final braking. For a small robotic lander, this is manageable. For a human mission needing to land 20 to 40 metric tons, it's a nightmare. That parachute trick does not scale. You'd need a parachute hundreds of meters across, so you need rockets for most of the deceleration. And every kilogram of rocket fuel you bring for landing is a kilogram you had to carry from Earth. NASA estimates that for every 1 metric ton you want on the surface, you need about 20 metric tons in low Earth orbit. That ratio should give you nightmares. But let's suppose by some magnificent effort we solve all that. Let's suppose we land a crew on Mars with everything they need. Now they want to come home. And this is where the universe really laughs at you. Because getting off Mars is in many ways harder than getting to Mars. Not because Mars has stronger gravity. It doesn't. Mars has about 38% of Earth's gravity. The escape velocity is only 5 km/s compared to 11.2 for Earth. But you're not on Earth anymore. You're on a barren, frozen, nearly airless world 55 million kilometers from the nearest machine shop. And you need to launch a rocket from the surface of another planet. If you bring your return fuel with you from Earth, you have to carry it all the way to Mars, land it safely, store it for the duration of your stay, and then use it to launch. And remember the rocket equation. Every kilogram of fuel for the return trip is a kilogram that had to be launched from Earth, transferred to Mars, and landed. The mass multiplier is staggering. Let's sketch the numbers. To get off Mars and head home costs about 6 to 7 km/s of delta V. With a good engine, your rocket at launch from Mars needs to be roughly 80% fuel by mass. That's 35 metric tons of fuel for a 10 metric ton vehicle. 35 metric tons of rocket fuel on Mars, where there is no fuel, and every kilogram had to come from Earth. Here's another way to see it. The total delta V for a round trip to Mars is in the neighborhood of 18 to 22 km/s. That's only a few km/s more than the moon mission, but the rocket equation doesn't care about your intuition. Going from 15 to 20 km/s can mean tripling or quadrupling the initial mass of the rocket. A Mars mission might require a spacecraft assembled in orbit weighing tens of thousands of metric tons. Nobody has ever built anything remotely close to that. But wait, there's more. The planets don't wait for you. Earth and Mars line up for transfer only every 26 months. If you land on Mars, you cannot leave whenever you want. You have to wait for the next launch window. The most efficient mission profile requires staying on the surface for roughly 500 days. The whole trip takes about 2.5 to 3 years. The long stay is not a choice. It's a consequence of orbital mechanics. During that time, the crew is exposed to cosmic radiation with no protective magnetosphere or thick atmosphere. Cosmic rays are high-energy particles that can shred DNA. They pass through walls, through hulls, through bodies. Over a 3-year mission, the cumulative radiation exposure significantly increases the lifetime risk of cancer. And there is no way to fully shield against it without meters of solid material which you cannot afford to bring. They are living in a habitat that must be self-sufficient because the nearest resupply is 9 months away, and you can't even send it unless the launch window is open. If something breaks, there is nothing anyone on Earth can do for months. If someone gets sick, there's no hospital, there's no evacuation, there's only the crew's own training and hope. Psychologically, 4 to 6 people in a habitat the size of a couple of shipping containers, isolated by millions of kilometers, with a communication delay measured in minutes for a year and a half, knowing that no one is coming to help if things go wrong. That degrades performance, strains relationships, and affects judgment. And those are risks you cannot engineer away. Now let's come back to the fuel problem. That 35 metric tons of fuel for the return trip had to be launched from Earth, survive the cruise, be landed safely, and be stored for a year and a half. The cascade of mass through the rocket equation is catastrophic. You need fuel to carry the fuel, fuel to land the fuel, fuel to launch the fuel from Earth. By the time you trace it all back, the total mass required is enormous. Not just impractical, but bordering on impossible with current technology. This is why some very smart people have proposed a different approach. Instead of bringing all the fuel from Earth, why not make it on Mars? This is called in situ resource utilization. Mars's atmosphere is 95% carbon dioxide. If you can crack that, you've got oxygen. If you can find water ice just beneath the surface, you can split it into hydrogen and oxygen and make methane. Methane and oxygen are a perfectly good rocket propellant. On paper, this is brilliant. You eliminate the need to carry fuel from Earth. The savings in mass are extraordinary. Instead of launching 35 metric tons of fuel, you ship a processing plant that weighs maybe 1 or 2 metric tons and let it run for a year, slowly filling your tanks with locally produced fuel. The rocket equation becomes much more forgiving because you've broken the chain. But making fuel on Mars is something we have never done. Not once, not even a small demonstration at meaningful scale. The chemistry is well understood, but going from a laboratory demonstration to 35 metric tons of fuel on Mars requires scaling up by a factor of millions. It requires a chemical plant operating autonomously in a hostile environment at temperatures that drop to 125 degrees Celsius with fine dust that gets into everything with no human maintenance for a year or more. And it has to work perfectly, because if it doesn't, your crew arrives to find empty tanks and no way home. And even if you solve the fuel problem, you still have to solve everything else. The landing, the life support, the radiation, the psychology, the 500-day stay, the 9-month voyages, the Earth re-entry at 12 kilometers faster than any human has ever come home before. Each one of these is a monumental problem on its own. Combined, they create a tapestry of difficulty that makes Apollo look like a weekend camping trip. I'm not saying it's impossible. I'm saying it's hard in a way that people don't appreciate. It's not a matter of building a bigger rocket or waiting for technology to improve a little. It requires fundamental breakthroughs in multiple fields simultaneously. It requires accepting risks that make the early days of aviation look safe. And it requires doing all of this with the knowledge that if something goes wrong, there is no rescue. There is just the crew, their spacecraft, and the vast, indifferent universe. The moon was a challenge. Mars is a crucible. The rocket equation ensures that every decision, every kilogram, every assumption is amplified into something enormous. It forces you to either bring everything or make everything, and both options push the limits of what we know how to do. That is the Mars return problem. It is not just a problem of going there, it is a problem of coming back. And coming back is where the universe shows you just how serious it is about keeping us here.